We're going to look at osmosis now, which is essentially the diffusion of water across a membrane. Now this is quite special because it seems to defy the laws that we've already talked about when it comes to diffusion. Osmosis doesn't tend to follow the rules as we understand them, and we need to look a little bit more closely at what's happening with the particle interactions to understand why water moves in particular directions across a membrane. Now, here we have a membrane, semi-permeable membrane, with water, and we've actually also got salt dissolved in there, but you've noticed here that the concentration of salt is different on both sides. Now, just like any other membrane, salts can't go through this membrane freely because they are ions. And if they're ions, they can't just go through unless they have a carrier-mediated protein to let them through. So these salts are essentially trapped either side of this membrane. Think of them as too big, but it's not always a case of too big, it's simply that the membrane will not let them through. Water, however, is small enough to go through, and it can do whatever it wants. And because it's moving around continually, a lot of the water will move across that membrane. So why do we see this after a bit of time passes? But there's already water on both sides of the membrane, and as you can see by the levels here, that there's an even amount of water on both sides of the membrane, just that one is saltier than the other. However, given time, this is what we would see. Over time, some of the water on the right-hand side here will actually move through into the left-hand side, and it will get to a point where the salt concentrations are actually even on both sides of the membrane because they're spread out the same direction. And once the salt concentration on both sides of the membrane is the same, the water will stop moving. Now, this seems to go against what we know, that water will actually diffuse across the membrane until it's evenly dispersed on both sides. But here, if the water level's the same, isn't it evenly dispersed already? Why did more move to this side than that side as soon as salt was added? Well, it comes down to understanding that water is not always free to move as it wants when other particles are dissolved in it. Water is a solvent, and when it has solutes dissolved in it, now these are charged particles, when it has them dissolved in it, they essentially collect and restrict the movement of some water particles, essentially making them not free to move at all anymore. And the more solutes you have dissolved, the less free water particles you have to actually participate in this diffusion. Now I'm going to zoom in so that you can get a clearer picture of what I mean. Here we have a picture of the water molecules with the solute in there. Now it looks like you've got the same number of water molecules either side of the membrane, but when you have solute dissolved in the water molecules, there is an electrical charge attraction or electrostatic attraction between the water molecules and the solute. That's why the solute dissolved in the first place, because weak hydrogen bonds have formed between the water and the solute to help pull it apart from its other solid parts. Now that means that these little molecules here, any that are close to the solute, are actually sort of joined to it by a weak hydrogen bond, and those water molecules are no longer free to move around and diffuse as they wish. The more solute you have, the more free water molecules have actually been caught up in this attractive force, which means they no longer can move around and participate in diffusion. So now we have less free water molecules, these are the free ones here, less free water molecules on this side compared to this side. Essentially their concentration of free water molecules is actually lower here than it is on the other side, meaning we now have a concentration gradient that looks like this. There is more concentration of free water molecules on this side to this side because of the solutes dissolved in it. Therefore, less are going to be moving in this direction compared to this direction. So water will move into this side of the membrane, and over time that will mean that water will actually build up on this side of the membrane and increase the level until the concentration of the salt particles is even on both sides. And so now the diffusion of water molecules is going to be even in both directions, meaning that those water levels will now stay the same. So because of that, we've given diffusion of water a specific name called osmosis, because water is not just affected by its own concentration, but by the solutes that are dissolved in it as well. They take up some of the water particles, reduce their freedom of movement, meaning essentially water's concentration is changed depending on its solutes. So osmosis is something you need to think about very carefully and take note of. Essentially it means that when salts can't move, water will move until the salt concentration is evened out on both sides of a membrane. Now this will change over time in a real cell, because we don't just have holes here, we also have carrier-mediated transport in our membrane that allows salts to move backwards and forwards until they even out on the sides of the membrane, if that's what the cell wants. But that takes energy and time. Water movement will happen a lot quicker than salt movement, so you will see an initial change in volume because of osmosis, but over time you'll see that volume start to go back as salts are transferred in and out of the cell in order to make the internal solute concentration of the cell the same as the extracellular environment. In real-life application, it looks like this. In order for a cell to not have water moving out of it or into it in uneven quantities, it's got to have the same concentration of solutes on the outside as it does the inside. If it doesn't, as we've just seen with osmosis, the water will move until the concentration of the solutes dissolved in it are even. So when a cell has the same concentration of solutes inside and outside, they're spaced exactly the same amount, we call that an isotonic solution, and this is how our cells like to exist. And that means that the direction of water movement is going to be even both in and out in this sort of situation. If a cell is placed in a situation where the concentration of the solutes are either more or less on the outside of that cell, then the cell's in a bit of trouble, because the water is going to either move in or out of it in order to dilute and keep the concentration of the solutes even. And this isn't always healthy for the cell. I always have one true story, unfortunately, that is perfect for this, and that's the story of Little Nemo. Now, many years ago, we had Nemos sold in pet shops because all the kids wanted to have a Nemo just like the movie. Now, Nemos are little saltwater fish, and unfortunately for Nemo, not everyone has a saltwater tank. Now, in order to survive in a salty environment, saltwater fish have a high concentration of salts in their cells to equal the salts that you find in the seawater. This means that because of osmosis, they are isotonic to their external environment. In other words, the concentration of salts in their cells is the same as their external environment, meaning that water will actually diffuse in and out at the same rate, keeping their cells at a safe volume inside and out. Now, a lot of people went and bought Nemos, and the people at the fish shop said, hey, you can't put these into a freshwater tank, you can only put them into a saltwater tank. Yep, we definitely will do that. Walk out of the fish shop, we'll just put them into our tank at home. So these people took these lovely little fish here and put them into freshwater tanks. Now, freshwater does have some salt in it, but not a lot. So these poor little Nemos were going into an environment where there was a lot less salt dissolved around them in the water than what they had in their cells, and their cells went into overdrive. Now, when you have more salt dissolved inside the cell than outside the cell, we say that the cell is in a hypotonic solution. That means the solution on the outside is hypotonic compared to the solution on the inside, which we call hypertonic. It's more concentrated. Now, because these salts can't easily move in and out of the cell, it takes active transport, the water takes over, because all of these salts inside the cell have taken up the free water molecules, essentially meaning that we have a concentration gradient now of water, which looks like this. So water will start to move into the cell at a greater rate than it's moving out of the cell. And what do you think happened to poor Nemo? The water moved into his cells, essentially blowing all of them up in size until they actually ruptured. And it doesn't stop until there is an even concentration of salt inside the cell compared to outside the cell. Unfortunately for poor Nemo, he died as a result of this. So this is a situation where cells can't survive because the external environment is different from the internal environment, meaning that osmosis works against them. In the case of Nemo, if you put him in a weaker external environment of concentrated salts, osmosis will mean the water will move into his cells. And I always think of it, when I think of it like this, hypotonic means he's blowing up. He's in a hypotonic solution. He actually has his cells blow up and expand into the point where he actually dies. Now, another version of that is the opposite, where you have a cell that's put into a hypertonic solution, which means the cell is actually weaker in salt concentration than its external environment. Osmosis will again work against that cell. In this case, the lower concentration of salts inside the cell means that this is hypotonic, and the outside, which has the higher concentration, is hypertonic. We've got a whole heap of salts outside, not a lot inside. All of the free water molecules out here are going to be reduced, which means we have a concentration gradient that looks like this for water. So water's not going to be happy. Again, it's going to start to move more in one direction than the other. But because most of the salt is on the outside and not the inside, the water movement overall is going to be out of the cell. And what's going to happen to this cell is it's going to end up shrinking and dying because all of the water has been sucked out of it. So the extracellular environment that you put cells in has to be isotonic. In other words, it's got to be even amount of solutes on the inside and the outside if cells are to maintain a constant amount of water going in and out, and therefore be able to maintain their cell reactions. If you have a huge amount of water moving out or into the cell, you're going to disrupt the cell to the point where you kill it. We see this in blood cells. Our blood is made so that the external environment, or the liquid of our blood, has the same amount of solutes in it that the blood cells themselves have inside. In other words, they're isotonic to each other. Just like this. the concentration of dissolved salts on the outside in the fluid, in a blood vessel, is the same as the concentration of the salts inside the cells that are inside the blood. Otherwise, the water won't be going in and out at the same rate. Now, if you drop blood cells into a hypertonic solution, which means the concentration on the outside is more, then the water is going to be sucked out of them via osmosis, and you actually have the cells going down and losing all of their volume. We call this flaccid. Hypotonic, on the other hand, is like this, where you have a higher concentration of salts inside the cell compared to the outside of the cell, meaning that more water will actually move in and swell them up and to the point of bursting. So when we are actually trying to store blood, we actually have to make sure that the external environment that we store it in is isotonic to whatever cells that we are looking at. It doesn't actually have to be blood, it's any type of cells. We have to put them in an isotonic environment to make sure that the cell volume is maintained, or you'll end up killing the cells. Now, believe it or not, plants actually use osmosis to their own advantage, and they actually like being a little bit overpressurized inside, because that's actually how they keep their shape. Now, if plant cells are in an isotonic solution where the water in and out is the same, they actually are a little bit flaccid because they don't have enough water in their cells to maintain the shape of their cell wall. They actually like to, and deliberately, make the extracellular environment hypertonic so that water is pushed into the cells to the point where they start to blow up a little bit. Now, in animal cells, our cells would rupture if they go into a hypertonic solution. As soon as they start to swell, they'll burst. But the plant cells don't, because around the outside they have a cell wall which stops them from blowing up too much. The cell membranes push against that cell wall so that they become nice and tight, and at this point we call that a turgid cell. In other words, it's nice, tight, blown up as much as it can, but it's not going to actually burst because of the cell wall. This allows the plant to maintain its shape because all of its cells are tightly packed and pushed out like this to hold the shape of the cell wall. This is what the vacuole in a plant cell is for, to help store a huge amount of water, to push the cell wall out, to push the cell membrane out, and allow the cell to maintain its shape. In order to do this, it means that the extracellular environment in plant cells has to actually be hypotonic or less concentrated to make sure that water is continually being pushed into the cells to the point where they are turgid. So plants actually use osmosis so that they can actually force themselves to get bigger than what they would normally be to maintain their shape. On the offside, if you actually put them in a hypertonic solution, say if I had a plant cell and I poured salt water over it, the water again would then be pulled out of that cell because it's a higher concentration of salts on the outside, and the cell membrane would then shrink just like we saw in the animal cells, and the plant cell will die. We call this plasmolysis. So there is osmosis in a nutshell. You're going to need to do some activities and some interactives to fully understand it. It does take a little bit of thinking and working through in order to completely understand and appreciate how this affects and how this is used by cells in order for them to survive.